Hi. It's almost 4th of July, so happy holidays. We have to talk about that soon too, because I'm going to Ohio for a week. So usually I'm very connected to my computer, but my parents are kind of old school and I don't think they have wireless. So I might be in a little bit of trouble or going to Panera a lot. I'll probably send you an email about that. Section 4.4 is on expectations of a random variable. That that so expectation or the expected value of a random variable is the mean of the random variable. What what value do you expect that random variable to take on average on the long haul? I think example one I put in there just because it's a nice, well, it's kind of a fallacy that people think when you say mean, that's how many should happen, every time unit. But mean is really an average over the long run. So again, on an average, you can have, well, variation, and so again, it's an average in the big picture. We also call it expected value. So expected value or mean, and the symbol we use is mu or e of x. I try in example two, what I'm trying to do is show you how the definition for expected value comes about. If you had 15,000 students, like this example here, and you were trying to find the mean number of courses they take, maybe 150 of them take one course, 450 take two courses, 1950 take three courses. So if you wanted to find an average, you would just add up 151s, 452s, and then, just add up how many of each of these you have and divide by 15,000. But if you look at that, that's really just the probability that one occurs times one, the probability that two occurs times two. So you're really just doing a weighted average, and it's not always the case that every value is equally likely. So this is out of 15,000 in every possibility, every one, and every. So again, I think the idea is important here that you really have a probability times the 7 times the probability 7 even occurs. So it's just a weighted average. So if you see, that's what I put in the solutions here. That's all we're really doing is we're taking the value 1 times the probability 1 occurs, 2 times the probability of 2 occurs. So that's the general formula here. You see it's just the sum of x times p of x over the acceptable x values. And so the notation is expected value of x, or you'll see mu of x. So interchangeably, I think sometimes I say mu, sometimes I say expected value, but they both mean the same thing, just different notation. Here's a quick example I made up. I can't say it's true. We are just finding here's the probability mass function for incomes of graduating Rose-Hulman students with CS degrees, and here's expected amount. And again, I made that up, so I don't know that that's true. So there's one example. What's the expected value of a fair die if you threw it 1,000 times one day and averaged all the values you get? The average would be 3.5. So it's just 1 times p of 1, 2 times p of 2, 3 times p of 3. Okay, this is just a fun example about Cracker Jacks. So you guys missed not being in class because we had Cracker Jacks this day and we got toy surprises, and that was the big fun of the day. So just a fun problem about expected value of winning a prize when they had a special promotion going on. But pretty much we figured out the toy surprise is still worth nothing. This is a nice paradox. This is just it's a game with expected value. It's interesting to read through. The paradox is that the expected winnings from this game are infinite, but I doubt when any of you read about the game that you were willing to pay an infinite amount of money to play this game. I mean, it's saying in actuality, on average, it's worth an infinite amount of money, but you're not going to pay an infinite amount of money to play this game. So that's where the paradox of this comes in. And I don't know if you want to look. I've done a paper or so on it. I like problems like this. It's called the St. Petersburg paradox. If you want to read more about that, or you want an interesting topic sometime to talk about. I just talk about a few properties. If a random variable is constant, it can only take on one value, then its expected value is that value. And so here's an example of that. And I think the most important thing, in fact, we are using this is going to be our last day in the regular class tomorrow. This we use probably more than anything in class. It's called I don't know if our book calls this, but everywhere I've ever gone or talked to, we call it the law of the unconscious statistician. And really what it's saying, instead of looking at the expected value of x, it looks at the expected value of a function of x, where a function of x could be sine x or cosine x or x squared or square root of x or ln of x. And basically what it says, if you take the expected value of a function of x, all you really need to know to find that expected value of that is the probability mass function for x times the function g of x. So it's very beautiful. This is one of the nicest theorems in probability. And so I do, highlight this is big deal. You'll be using this throughout the course. I'll be using it to prove other theorems. So here's just a quick example. For some reason, maybe we want y to be the square of a die roll. And if we squared a die roll, here are all the outcomes we could get. And each of them have a probability of 1/6 still. And if I wanted to find the expected value of y, where y is a square of a die roll, we get 91.6. So all I'm doing is multiplying. Wow, that really messed it up. I'm multiplying 1 squared times p of 1, 2 squared, times the probability of 2 squared, 3 squared times the probability of 3 squared. So the nice thing, wow, that really looks bad. It's just 1 times p of 1, 2. Okay, but, I mean, we could have used, well, actually, sorry, I did cut. So this is expected value of y, sorry about that. All I would multiply, this isn't law of unconscious, just y times p of y. So 1 times p of 1, 4 times p of 4, 9 times p of 9. But if I use the law of the unconscious statistician, and you're going to say, wow, this doesn't look any different to me, it says I can take x squared times p of x. So expected value of x squared is 1 squared times p of 1, 2 squared times p of 2, 6 squared times p of 6. Very nice. It's just, I don't know if you see the difference between these two methods. Here I'm using the distribution of y, and I had to figure out what y was, but here nicely I can just stay in x's, and I never have to convert to y if I don't want to find expected value. So example 9 is a nice expected value of 2 to the x. I'm just going to use the law again. A couple other properties. Expected value of a linear sum is the sum of the expected value. Sorry, the sum of the expected values. Yeah, so expected value of a linear combo is a sum of the expected values. So I just show you, okay, yeah, and constants come out for free in front. I think that makes sense. I didn't prove it. Here's another just fun example of an expected value. Two guys shooting at each other, keep spinning the barrel. So every time there's a 1/6 chance A will shoot B, there's a 1/6 chance when they pass it over. And I'm just asking for the expected number of trigger pulls on average before one of the two hits the other. We'll imagine they're just paint bullets or something like that. But so another nice problem, and I think what's cool about this is you would end up using Calc 2, the idea, we talk about these kind of sums, and you can use it to compute this value down here, or you could go to Maple in this class, but it is nice that we use some Calc 2 facts. Okay, so I'm going to do I think a video now on 4, 5 variance. If you know mean, you should know variance, and then maybe just one other tonight.